Hello everyone. In 4.2, we're going to be looking at a particular discrete probability distribution called a binomial probability distribution. So a binomial probability distribution is a discrete probability distribution that allows us to model the probability of observing some R number of successes in N trials. So if X, which remember capital X represents our random variable, is a binomial random variable, then X represents the total number of successes out of the N trials. So for example, X is equal to, so we do curly bracket because it's a set with the possible outcomes, we could get 0 successes, we could get 1 success, we could get 2 successes, and we could get up to N successes. Now, note, the definition of success is relative. And the reason I want to bring this up is because when we talk about success, we talk about the successful outcome that we're looking for, the outcome that we're interested in. So sometimes success actually might be failure. So if I'm looking for faulty parts in some manufacturing process, I'm looking for fault, meaning that if I find a faulty product, then I have succeeded. So just be careful when I say success, what I really mean is the outcome of interest. Okay, so this might be, for example, if this is the number of students that fail an exam, your failure is not a success, but in this outcome, we're considering it as a success of the condition of interest. Now, let's actually define a lot of things about binomial distribution. And the first is that X is a binomial random variable, which means that it has the outcomes, of course, of the number of successes. So if we have some N of equal to 20, so 20 possible outcomes, that means that you can have 0 successes, 1 success, 2 success, up to N number of successes. And I said N number of outcomes. What I meant to say was N number of experiments or trials, depending on how you want to view it. Right, so for example, if I'm flipping 20 coins, there will actually be 21 outcomes because I could get 0 heads, I could get 1 head, I could get 2 heads, I could get 3 heads, all the way up to including 20 heads, where every coin flip is heads. N is our total number of trials. So in this case, X is our binomial random variable. N is the number of trials R, or X, is going to be the number of successes. Now you might wonder, why do I have 2 different letters here? And it actually just has to do with convention. So oftentimes we will use R to represent the rate of success. So for example, 4 successes, 6 successes, stuff like that. But it's still X. X is just a way of representing the outcome of a random variable. So whenever we're doing these probabilities, oftentimes we'll write it something like this. The probability that the random variable X equals the outcome X. So an example of this might be if I'm flipping 15 coins, it might be, what is the probability that my outcome is equal to 3, something like that. So oftentimes, because we represented our set as capital X, we oftentimes will just use X as our random variable, our actual outcome. But oftentimes in books and things like that, you will see R just represent like the rate. Now, we also have NCR, which if you remember from prior class, I'm going to be writing as NCR. This is the combination of choosing R objects from N total objects where order does not matter. And then just a quick recap on that, if you remember that NCR is just equal to n factorial divided by n minus r factorial times r factorial. Now, if you're using a calculator for this, most calculators can do a combination. If you're using a TI-30XA, what you're going to do is you're going to put your n value. Let's say you wanted to do something like 10, choose 3. You're going to hit 10. You're going to hit second, which is at the top left. And then above 8 or 9, you're going to see the symbols for NCR and NPR. So for a combination, you want to hit the NCR button. And then you're going to put 3. You're going to hit equals, and it's going to give you that combination. If you have, for example, a TI-30X2S, yours is going to be a little bit different. You're going to still hit that 10, but then instead of hitting second, you're actually going to have a button near the top left which says PRB for probability. And you're going to see NCR, NPR, and a factorial symbol. You just hit your arrow over to the NCR, hit equals or enter, and then you put your 3, hit equals or enter again. That will give you your combination. If you have some other calculator, you'll have to do it some other method. But you can usually just use a calculator for this part. But if you wanted to calculate it by hand, we did show that previously, how to do that. And this is the formula that you would use. We also have P, which is just our probability of success. And then we have Q, which is our probability of failure. Now, because we only have 2 possible outcomes, success or failure, this is actually just going to be equal to 1 minus the probability of success. What this means is that if I have a coin that is weighted and I have a probability of getting heads of 0.6, and that's my success, so I have a P of 0.6, that means that my probability of not getting heads or not getting a success, which would be a failure, would be 1 minus 0.6 or 0.4. So using the binomial probability, we can find the probability that we observe our successes out of n trials. Now let's talk about the assumptions of our binomial distribution. You may recall that I mentioned previously that anything we do in statistics has certain restrictions or assumptions that are made about this method, distribution, things like that. So the first assumption is that there's a fixed number of n trials. So what does this mean? It means that if I am flipping 20 coins, we're assuming that that number is fixed. It has been determined ahead of time. And this is because if you go and actually look at like binomial tables, you will see that there's actually an individual table for all of the different possible n's that you have. And that is because every n is actually associated with a different binomial probability. So the binomial probability of n equals 2 will be a different distribution than when n equals 3, than when n equals 4. So we assume that there is a fixed n number of trials. And in each trial, there are 2 possible outcomes. So that means that I have a total of n trials that does not change. And every single trial, which is every individual part of it, has 2 possible outcomes. So this could be something like, again, flipping coins. If I'm flipping 6 coins, n is equal to 6. The first coin flip has 2 possibilities, heads or tails. The second coin flip has 2 possibilities, heads or tails. Third coin flip, heads or tails. Fourth coin flip, heads or tails. Fifth coin flip, heads or tails. Sixth coin flip, heads or tails. The second assumption is that the outcome of the n trials are independent. So this means that we're assuming that when I flip that first coin, it has no impact on that second coin flip. It has no impact on that third coin flip, or that fourth, or that fifth, or that sixth. They're independent from each other, meaning that the probability does not get affected by what came before it. The third assumption is that P is constant, meaning that our probability of success does not change between trials. So whenever I set that probability of success, if I tell you I have a weighted coin with a probability of heads of 0.6, that means when I flip one coin, it's 0.6. When I flip my second coin, it's 0.6. When I flip my third coin, it's 0.6, and so on for every coin of your n trials that make up this binomial distribution. So note that when we're doing this, when we talk about having two outcomes, I'm going to use heads and tails for coin flips oftentimes because it's easy to wrap your head around, it's easy to think about. But this could be something like flipping a coin, heads or tails. You could think of it as success or failure. It could be true or false, on or off, faulty or not faulty, works, doesn't work. It's anything with two possibilities, possibility A and not A, which would be possibility B. So for each probability, since P is constant, that of course means that also, which this isn't really a rule, but it's a part of what happens because of this rule, Q is also constant. Now you might wonder, what if one of these or more of them are not true? Well, in that case, you would actually need a different distribution. This distribution is very specific about it only works when you have a fixed number of n trials, which have two possibilities per trial. Your trials are independent of each other, and your P, or your probability of success, is constant. Now, remember how I mentioned that the different number of n would actually be a different binomial probability? This is actually why when we write a binomial, which you won't write it this way, but this is actually how we write it, is it's capital B for binomial, it's n, comma, P, semicolon, R. And what this means is that this is a way of symbolizing that we have a binomial distribution with this number n, this number P, and then based on that, we can find different probabilities of R, which if you remember, R is just our outcome. And R can be anything from our sample space, which is equal to 0, 1, 2, ... up to n. Now, the way that you'll actually write this is you'll usually just write something like probability that x equals whatever that value R is, or more likely, what most people are going to do is just going to be, what's the probability of getting R? But this is actually what we're solving for. And the reason this part goes before the semicolon is that this represents that this is what's telling us which distribution we're actually using. So if you go to Appendix 2 in your Pearson book, you actually can find tables. If you scroll down to the binomial table, you'll actually see that there are a bunch of binomial tables. And this is going to be basically where you're going to have n equals 2, and you'll have a table for it. N equals 3, you'll have a table for it. N equals 4, you'll have a table for it. And then along the top of that, it will be some different probabilities P. Every one of those n and P combinations is actually a different binomial distribution, meaning that this has to be something that is done before you actually start solving your probability. Now let's actually discuss how we can actually solve these binomial probabilities. So the central problem of a binomial experiment is to find the probability of getting R number of successes out of n trials, where if you remember, every single trial has two possible outcomes with a probability P of success. So the probability of an experiment of n trials will have R successes follows binomial distribution, which as I said previously, this is going to be B, n, comma, P, semicolon R for binomial probability with n and P, which will set up what binomial distribution we're in, and we're looking for R number of outcomes, which we're just going to write as P of R. This is going to be equal to n, choose R, P to the R power, 1 minus P to the n minus R power. Which, breaking this down, what is this doing? Well, this P is our probability of success, and we're looking for the probability of R successes. So we're saying that we have R number of successes. So what's the probability of being a success? And we're taking that to the R power. 1 minus P, which of course you could also write as Q, is the probability of failure. Now, if we have a total of n trials and we have R successes, that means we have n minus R failures, right? So if n is 20 and R is 12, that means that 20 minus 12, or 8 of the outcomes, have to be failures. This n choose R, if you remember, is just another way of writing n CR, which is taking the combination of n objects and how can I select R number of those objects where order does not matter. Now, one thing I want to talk about briefly is, where does this term come from? We'll go to the first part in a second. But where does this term come from? So let's actually do a really quick example. Let's say that I have a probability of success of 0.7, and I'm going to flip 3 coins, let's say. So I'm going to flip 3 coins. And this probability of success P might be getting heads. So if we were to create a tree diagram, a probability tree diagram of our experiment, this would be, I'm going to flip a coin, and I can get heads or I can get tails. And my probability of getting heads is 0.7. My probability of getting tails is 1 minus 0.7, or 0.3. If I get heads, I flip another coin, I can get heads or tails, 0.7, 0.3. If I had gotten tails, I would also flip another coin. I can get heads or tails, 0.7 or 0.3. If I get heads, I could get heads or tails, 0.7, 0.3. If I had got heads, tails, I can get heads, tails, 0.7, 0.3. If I get tails, heads, I could get heads or tails, 0.7, 0.3. And if I get tails, tails, I flip another coin, I can get heads or tails with probability 0.7, 0.3. So these are all my possibilities. And you remember from probability tree diagrams, I can follow the branches. I can get heads, heads, heads. I can get heads, heads, tails. I can get heads, tails, heads. I can get heads, tails, tails. I can get tails, heads, heads. I can get tails, heads, tails. I can get tails, tails, heads. And I can get tails, tails, tails. For a total of 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. Now, let's say that I wanted to know what is the probability that I get 2 heads. So if you were following these branches, you would look for ones that had 2 heads. So if I went heads, 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 does that have 2 heads? No. Heads, heads, tails. This one does. So I'll put a little dot here. Heads, tails, tails. Nope, that only has 1 head. Tails, heads, heads. That one has 2. Tails, heads, tails. That one does not. Tails, tails, heads. That one does not. Tails, tails, tails. So in this case, my probability of getting 2 heads is just going to be 2 out of the total 8. Now, you might think, why don't we just do it this way? Well, because binomial probabilities will work for when we have much larger experiments. I'm just doing this as a very simple example to show you. Now, if I asked you to solve this, though, you would have to look at, first of all, what are all of my possibilities? Well, if I looked at my first branch, this would be the case where I have probability of success, so I got 0.7 of this occurring times 0.7 of this occurring times 0.7 occurring. So this is the probability of getting heads, heads, heads is 0.7 times 0.7, 0.7. Probability of getting heads, tails, or heads, heads, tails would be 0.7 times 0.7 times 0.3. Probability of getting heads, tails, heads would be 0.7, 0.3, 0.7. Probability of heads, tails, tails would be 0.7 times 0.3 times 0.3. And basically what's going to happen is, if you were to take all of the cases where we get 2 heads, which we said were these 2, notice what our probability is. 0.7, 0.7, 0.3. The second one, 0.3, 0.7, 0.7. So every outcome where P, because P is constant, where I get 2 heads has 0.7, 0.7, 0.3. Now, I could replace these numbers, though, because if you remember, 0.7 is P. 0.3 is 1 minus P, or Q. So I could actually rewrite this as P times P times Q, or P squared times Q to the 1. And this is actually where that second part of our binomial comes from. It is the probability of success to the power of the number of successes which would cause this to be true. 2 successes. Times the probability of failure to the power of how many failures I would have to have for this to be true. Well, if I follow this first branch, I have 1 failure. If I follow the second branch, I have 1 failure. I have 2 successes on each of them. So all it is it's just your P times P times P for however many successes you have. Now, the reason that we have this first term, though, is then we say, okay, But I don't care about repeats. I just want to know how many ways can I get this. So what we do instead is now we take the combination because we're not looking for repeats. So basically what we do is we divide out all the repeats. So looking at this example we did, we had 3 for our n, right? Because we flipped 3 coins, this means n equals 3. So this would be 3 choose 2. Which would be 3 factorial over 3 minus 2 factorial times 2 factorial. This is going to be and this will be, I'm just going to do 3 times 2 times 1. This 2 is going to cancel with this. 1 times 1 is just going to be equal to 1. So this is going to be equal to 3. You might wonder, why is that? It's actually because when I was doing this tree diagram, I actually forgot one of the examples, which was heads, tails, heads. This one was also the number of outcomes. So we had 3 outcomes that were successes. This is really what it's just telling us, is that we're getting probability of heads times probability of heads times probability of tails, and then we have 3 of them. This tells us how many of the total outcomes. Now, of course, the reason we might want to do this binomial is because, again, this could branch off many times. So, right, so for example, if I said that my n is equal to 142, you're not going to want to draw a probability tree diagram for 142 coin flips. You can see that even just drawing it for 3 is already kind of getting crowded. If I did it for 4, 5, 6, maybe even, sure. But 142, that would be huge. So what we do instead is we use this. We say, okay, well, we have the probability of success to the power of how many of those successes we have, times the probability of failure to the power of how many of those failures we have. And then we figure out how many of our total branches would give us this many successes and this many failures, where we don't care about order. And then at that point, this will give us our binomial probability. Next, we're going to talk about how can we find our mean or expected value of our outcomes and the variance and standard deviation for this binomial probability distribution. Now, if you remember from 4.1, we have a way we can find expected value, variance, and standard deviation for any discrete probability distribution. The problem with those, though, are if you actually looked at something like, for example, the expected value, and this, of course, holds true for all of them, I would need what? I would need every possible outcome, which we have, that's easy enough, and its associated probability. Meaning that if you wanted to use expected value for a binomial, and let's say that our n was 142, you would have to find 142 plus 1, because you have to take into account 0 successes. You would have to find that many probabilities. So let's look for an easier way. And the way we do this is that for specifically if we have a binomial probability distribution, we can find our expected value of x using n times p. Now you might wonder, why is that? Well, let's say, for example, that I have 20 coin flips. And I have a probability of success of 0.4. How many successes would you expect there to be on average? Well, in this case, it would be 20 times 0.4, which would be equal to 8 heads. I would expect on average, if my success condition is heads, I would expect on average that I would get 8 heads. This is giving us, again, the center of this data based on the weighting by this probability of success. To put it more into perspective, let's just say something easy. I have 10 coin flips. If I have a weighted coin with a probability of success of 0.9, how many coins do you expect to get heads? 9 of them, right? If I have a probability of success of 0.2, how many heads do you expect on average? 2. It's basically just telling you where is the most likely outcome to occur. And it's going to be based on this probability of success. The further you are from 0.5, the more that it's actually going to skew your results. So for example, if I have something like p equals 0.2, this means I'm going to have a graph that looks something like this. Something like this, where if I were to kind of draw a line to represent it, you will see that in fact it is skewed to the right. If I have a p of 0.5, then I would expect my largest value to be right in the center, and I'm going to have something like this. Where if I were to draw my distribution line on top of it, it's going to be nice and symmetric. And of course, if I have a p that is much bigger, let's say p equals 0.9, then I would expect most of my outcome to be on the right, and then it's going to get more and more and more outcomes to the left. They get smaller and smaller, and I'm going to expect a left skew. Now, we will talk more in depth about this later, but basically what I wanted to tell you about is this point right here, that highest point, that is your expected value or your mean. It is telling you what is the location of the most likely outcome, and it is going to be based on your probability of success times the number of trials that you are actually performing. So again, if I have 100 trials and I have a probability of success of 0.9, I expect on average 90 successes. If I have 100 trials and I have a probability of success of 0.6, on average, I expect around 60 successes. So to find our expected value for binomial probability, instead of finding the probability of every single possible outcome, all I need to know is how many trials am I performing and what is my probability of success on each of those trials. Now, for our variance, it is just going to be n times p times q. So again, take your number of trials, multiply it by the probability of success, multiply that by the probability of failure. And of course, if you want your standard deviation, it is just going to be the square root of sigma squared, which is going to be equal to the square root of n times p times q. So if you know that you're working with a binomial probability distribution, this is actually a lot simpler than the method you learned in 4.1. Now, 4.1 works for any discrete probability distribution, but it does involve a lot more numbers and calculations. This is specifically for when you have a binomial probability distribution. And if this is true, then all you need to solve it is you need to know what your number of trials is, and you need to know what your probability of success is. And from that, because we know p, that means we also know what q is, because just remember that q is equal to 1 minus p. And this will give us our expected value, or our mean, our average, our standard deviation, and our variance. Remember, variance is the square term, standard deviation is the square rooted term of variance. Now, the last thing I want to talk about right now is going to be how do you translate from the English words that we use in our problems we're going to give you into math. And here is a slide to kind of give you an idea of some of the terms you might see, which will help you kind of break down the types of problems that you're actually solving for. Right? Because oftentimes we're going to give you these binomial distribution problems in terms of a word problem. So for example, if you see words like at least, no less than, and maximum of, these are all ways of saying greater than or equal to. So for example, I might say, if I'm flipping 20 coins, what's the probability I get at least 19 heads? Or what is the probability I get no less than 12 heads? Or what is the probability of, and I want to point out that this last one, instead of maximum, should have said minimum of. What is the probability I get a minimum of 17 heads? So the second one, we have more than, greater than, or larger than. These are all ways of saying greater, right? So if I said, what is the probability of getting more than 4 heads? That means everything that is more than 4, but not including it. I could also say, what is the probability my number of heads is greater than 4? Or what is the probability that I have a number of successes larger than 4 when I'm flipping a coin? Something like that. These are all ways of saying greater than, but not including. Now, the reason this is important is when we have discrete data, if I say greater than or equal to, that means that it is everything from that point up. If I say that it is, so this is greater than or equal to, if I say greater than this point is not included. that is the same thing as saying everything that is greater than or equal to the point that is above it. And this is super important because in discrete probability, probability of x greater than or equal to 4 is not the same as probability of x is greater than 4. And this is because 4 is not included. There's nothing between 4 and 5. So therefore, this is the same thing as just saying, what is the probability that I get a value that is greater than or equal to 5? And when you're doing discrete probabilities, you always have to start with whatever your equals to is. You can't have a greater than 4 because 4 is not included on it. So you'd actually be starting with probability of 5, probability of 6, probability of 7, up to your probability of n. If you see fewer than, less than, or smaller than, these are all ways of saying less than, right? What's probability I get, fewer than 2 heads? What's probability that my number of heads is less than 3? What's probability I get a value smaller than 4? Things like that. Those are all ways of saying less than. Next, we have no more than, at most, or maximum of. So what is probability that I get no more than 4 heads? What is probability I get at most 4 heads? Or what is probability I get a maximum of 4 heads? These are all ways of saying less than or equal to that number of heads. And the next one is, and the last one is exactly, equal to, or is. These are all ways of saying equals. So what is the probability that I get exactly 5 heads? What is the probability that my number of heads is equal to 6? Or what is the probability something is 6, right? So it's like, what is the probability that the defective units are 6? So it could be is or are, depending on context. So these are some of the ways that you are actually going to see us write to determine what kind of probability we're actually looking for. And in the next video, we'll actually start doing some examples to show you all of these kind of problems you might see and the language that we use in them. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.